All right. Good evening. Welcome to the November edition of the St. Louis Java Users Group. My name is Zachary Klein. I'm on the steering committee of the user group, and I'll be your host this evening. Before we open it up for our speaker, I won't go through the whole list of the history. Most of you have been here before. We've been around for a while. Of course, attendance is free, so please come and join us whenever you can. There will not be a meeting next month. That's the most important announcement. We don't hold a meeting in December, but otherwise, second Thursday of each month, join us for food. Yes, typically at 6 p.m. It's not here yet. Apparently, the pizza shop is a bit backed up, but there will be something eventually. So appreciate your patience. I think there's some extra Halloween candy in the back, so maybe I'll bring some of that in to hold us over. So food and social at 6 p.m. and then the meeting typically starts at 6:30 p.m. We apologize. We've had some technical difficulties this evening, so we're a little bit behind schedule. And our meeting location is right here, so you've made it. Congratulations. Here at OCI in the training room, and then of course streaming online. And this will be recorded to Bruce's YouTube channel, so you'll be able to revisit the presentation afterwards as well. That's the steering committee, myself, Zachary Klein, Bruce Alspaugh, Robert Levitt, and Ted Doyle. And you can reach us all on the steering committee at the email address there at the bottom of the slide. Our sponsors, OCI, my employer, the company that hosts the training room here, Manning Publishers, JetBrains, and our friend Lee Bobbitt, who has graciously sponsored our meetup subscription. So we appreciate that very much. Announcements. We continue to have our regular discount code for Manning eBooks, 45% off. I think it's just eBooks. Is that correct? Yeah. So use the discount code there. And our speaker, Haoyi Li, is actually sponsoring the pizza, which is to come. But we're very appreciative for that. So thank you. And we are always looking for more sponsors. So if a recruiter is watching this online, the recording, please get in touch. We would love to have you sponsor our meetings. And check out the meetup page, of course, to see updates and upcoming presentations. I don't know if we have anything for next year on the schedule yet, but we are working on that. So, and then past presentations, as we said, are uploaded to YouTube. So you can see the link there on the slide. So tonight's presentation, Simpler Java Build Tools with Object-Oriented Programming by Haoyi Li. Without further ado, please welcome our speaker. Haoyi, take it.
Cool. Hi, everyone. Let's see. Here's my slides.
Looks like I threw the light off.
Okay. Hi, everyone. So this presentation is about Java build tools. So the motivation for this talk is that although Java is known to be very easy to learn, very easy to use, very performant, and have very good IDE support, Java build tools like Maven or Gradle don't always live up to that reputation. So this talk will explore why are Java build tools hard from a user perspective sometimes? Why are they also hard from a build tool implementer perspective? That's why it's not so easy to just make a new build tool. We'll talk one of my open source projects, which is called Mill, which tries to explore this space. And one of the interesting ideas behind Mill, which is this idea of object-oriented builds that really tries to simplify how build tools work. So about myself, I've been programming about 20 years. I've been working on open source projects since about 2012 or so. My last job was at Databricks, which is a Scala on the JVM shop. So a lot of my Scala JVM projects, but also a lot of Java projects and other JVM technologies. My professional expertise is in developer tools. So everything from your dev environment, your CI system, your build system, and everything before your code goes to production. Today, we're talking about build systems. So the first part of this talk is why are build tools hard from a user perspective? And to me, that comes down to the three areas of performance, IDE support, and usability. So one example is when you talk about Java tooling or Java like the developer experience, people often think of it as kind of a bit slow, a bit hard to use, a bit clunky. This is in contrast to maybe people using scripting languages like Python, where you just change your code, it runs instantly, or languages like Go, where you change your code, you hit compile, and by the time you can press another command, it's already finished compiling. In contrast, Java often feels a bit slow and annoying to use. So if you take a code base like the Netty code base, which is a big open source project, 500,000 lines of code, clean compiling the whole thing in parallel on my laptop takes about 50 seconds to a minute. I can kick this off now. Go to my terminal. So we're not going to wait for it. It'll take about a minute or so. And this is about what you expect working with typical Java projects. Like you run compile, it takes a while to run, maybe it finishes, but doesn't feel snappy. Even compiling a single module within the Netty code base, in this case, a Netty common module, takes 4.5 seconds to compile 29,000 lines of code. So is this fast? Is this slow? It doesn't feel very fast. It's like waiting for your terminal to run. You have to add a print line or remove some debugging statements. What people don't realize is a lot of this overhead is not the Java compiler itself, but just the build tool sitting on top of it. So if you add the -- debug to see what Maven runs internally, and you just run that yourself, you'll see that it runs Java C with this very long class path that I can't fit on the slide. And it completes in 1.5 seconds instead of 4.5 seconds. So of the 4.5 seconds, 2/3 of it is just build tool overhead, and maybe 1/3 is what the thing you're actually trying to do, which is compile your code. And if you've worked with Java for a long time, you may know that this is the worst possible way you could get performance out of a Java program, like the Java compiler. But the Java compiler is written in Java. It runs on the JVM, which is known for slow startups and gets performant later when it warms up and has time to optimize. So, and if I try and measure the actual good performance of the Java compiler, like in a hot, long-running daemon, like how Java programs are normally run, you see that it compiles the same code, same source file, same dependency, same Java version in Java compiler, but runs 5 times faster than using Java C from command line, which was already 3 times faster than using Maven. So now we are 15 times faster than Maven without actually doing anything. Like we didn't rewrite Java compiler in Rust. It's the same compiler, just used properly with a long-running program. So I can show you this live. So earlier I kicked off a clean compile of the whole Java code base. Took about 1 minute here. You see 1 minute, 03 seconds. I make this a bit bigger maybe. If I run a clean compile of the common module in Netty, so first I just clean it to make sure it's I'm not just relying on the cache. It takes about 4.5 seconds to compile that 29,000 lines of code in that one module. If I run Java C with this very long command line that you probably won't run yourself, but you can. You see it takes 1.4 something seconds to do the exact same thing. And if I run this benchmark that does this in memory, so I can show you what this is. All this is a single file Java application with a main method. It has a while true loop, and it runs the Java compiler over and over without any caching. So it's just a clean compile over and over, but allowing the compiler to warm up. So if I run this, the first time it takes more than a second still because it's the same as the Java C benchmark we saw earlier. But as it runs, you see the duration in this bottom left gets shorter and shorter as the JVM warms up. And that's what you know, right? The Java virtual machine starts off cold, slow, but warms up and gets performant later. So after a few runs, we're taking about 300 something milliseconds to compile the same 29,000 lines of code that we were taking 4.5 seconds earlier to compile using Maven. So compiling Java isn't the only thing that you do in your day-to-day work, but this is just a kind of demonstration of how much overhead the build tool adds over what's actually quite a fast underlying platform. Like Java is very performant, but once you add on a bunch of like Maven overhead, Gradle overhead, they actually can become a lot slower than we expect. And not just for compiling, but for testing, packaging, deployments, and so ID support, and so on. So that's a compilation, that's performance angle. The next thing I'm going to talk about is the ID support. So all build tools have ID support. Java is known to have good IDs from IntelliJ to VS Code, not VS Code, to Eclipse and NetBeans and so on. And all of these do have build tool support, but it often isn't as good as you'd expect. So if I open up over here, I have the checkout of the Mockito code base. So Mockito is a popular unit testing library. It's built using Gradle. Here's an example Gradle config for the error-prone submodule within Mockito, one of its 20 submodules. It uses the Groovy syntax, but you see there's ID support with syntax highlighting. I can pop up definitions and stuff to some extent. But where this falls down is if you try and like jump to things, you find that you can't get anything useful. Like I jump to test implementation, I get this dependency handler stub. I jump to JVM args, I get this getter, I get this setter, but I don't get anything else. I don't see what the value was there before. I can't see where the value is being used later within the build system. So, if everything's working perfectly, you copy paste something off Stack Overflow and it works out right out of the box, there's nothing wrong. But when things do go wrong, it can become very difficult to debug your build system when the IDE basically doesn't help you. You can't see where these values are being used. You can't see what you're interacting with. You can't see what they were there before you modified them. You basically can't see anything about your program. And it's not just JVM args, but compiler args. It's the same thing. Try to jump to Java doc. It's kind of the same thing. All of these, you have some IDE support, but it's not as good as you'd expect. And this is in contrast with actual Java code, right? Like if I open up a random file within the Mockito code base, anything on this screen I can jump to and find something useful, not just the documentation, but this implementation. I can recursively navigate through this program to see what it does, and also use the IDE to find usages to navigate downstream to see where this thing gets used later on. All of these are things I can't do in my build tool. And you ask, why is that, right? Like this is Java code. This is also Java code, and this is the same IDE, it's IntelliJ. But the problem is the build tool, it works. In this case, Gradle works by setting these global mutable variables like JVM args or compiler args. And just because they wrapped in a getter or setter doesn't make them any less global or any less mutable. And if any of you use global mutable variables in your application code, you know that you can't really navigate around your global mutable variables using your IDE because IDE can't figure out where the value is coming from or where it's being used. And that's the experience we get in the build tool, like in Gradle. In contrast, most Java programs like this example test file in Mockito code base doesn't use global mutable variables. It uses objects, classes, methods, overrides, all things that IDEs are very good at. And that's why, despite being the same IDE and the same language, build tools like Gradle and to some extent Maven and others have a very poor IDE experience and makes it very hard to work with interactively in your editor. So that's IDE support angle. I showed you the Gradle Groovy syntax. The Gradle Kotlin syntax is a bit better with types from Kotlin, but it's largely the same problem. And the Maven build tool using XML has a similar problem in that if I look at property regex, I want to jump to it and see where it's being used, how it affects the program, maybe something's misbehaving, I'm trying to figure out why. I just cannot. It's a black box that I have to copy paste something or ask ChatGPT to copy paste for me. And there's no way I can figure it out myself. So the last thing I'm going to talk about is usability. So there are two angles to usability. One is usability in the small programs getting started. One is usability in large programs where you need to maintain and customize and tweak your build tool. So for basic usability, let's say I have this small program. So this is a complete Java program that scrapes Wikipedia using its HTML pages and just does a breadth-first search over the Wikipedia article graph. So the main method, you see you have your breadth-first search scene and current sets. I have a for loop for up to the current depth that fetches all the links from each layer, adds it to the next layer, and does this layer-by-layer breadth-first search. And it uses this JSoup library to do so. So if I did not use a JSoup library, I could just run java html.scraper.java from the command line and just work out the box. That's very convenient. But now that I have this JSoup library, I can't do that anymore. So what can I do? I could use Maven, but it's kind of annoying to set up Maven just to have this small script. Like let's say I wanted to create a Maven config. Who could do this without copy pasting it from somewhere? You just type out the Maven config for this pom.xml file. In theory, you could, but in practice, you probably can't. Because it looks something like this. It's not rocket science, but it adds a lot of friction for just, I want to run this Java program and do something, which you don't have in other languages like Python or Ruby, where you can actually just run things from command line. And even the command line to run it is kind of awkward. That you can't just run Maven, like run. You have to say Maven exec :java -d exec.args and put the thing in quotes. And each of the args itself needs to be quoted. They need to escape the quotes for double-layered quotes. And it's generally a whole thing where I just want to run this program and get out of my way. So even for getting started is pretty difficult using Maven and Gradle and other Java tooling. But that more advanced use cases also surprisingly difficult. So any project that grows needs to customize a build tool. Like the Netty project we saw earlier needs to compile C code using GCC or Clang. The Mockito project needs to do some bytecode class file manipulation, kind of bespoke. So as a representative example, let's say I want to save the project line count as a TXT resource file to use at runtime. So it's kind of contrived, but it's representative of the many things that you have to do in a real big project. So doing this in existing Java build tools is not impossible, but it's surprisingly tricky. So here's an example, a config using the Maven exec plugin that tries to do this. And it doesn't work on Windows, that's one. So any of you who use Windows, this won't work because Windows doesn't have SH built in. There are also 2 bugs here that let's see if anyone can spot. Yes?
What if you use something like Haoyi or Git bash?
I think that would work. Git bash or, yeah, so those will work, but normal PowerShell or CMD would not. But beyond that, even on Mac OS or Linux, there are bugs here. And this is the simplest Java build tool config. Let's see if anyone can spot the bugs. So one bug is we forgot to escape our ampersands because this is not just XML, not just bash, but bash embedded in XML, and XML ampersands need to be escaped. And there's another bug in that we forgot to escape this little arrow here because this greater than sign is an XML special character, needs to be escaped by ampersand GT semicolon. So it's not like rocket science, but this is really the hello world of build tool config. Like if I ask a new grad to count the lines walk the lines of code in a folder, read the lines and count them up, it should be like a 5-minute zero failure task. But with a build tool like Maven, it can be surprisingly tricky. And there are other ways to do this, whether it's a Maven plugin or Ant scripts or whatever. But all of these are tricky given how simple and trivial this should be. Other build tools like Gradle have different problems. So Gradle, it runs on the JVM. You're writing Kotlin or Groovy. In this case, it's a Kotlin syntax for Gradle. So you don't have XML problems. You don't have Windows problems. It's cross-platform JVM. But you have other problems like needing to register the depends-ons and inputs and do last or do first and needing to know which one to use. Also quite tricky. So there's also a bug in this one. Let's give you like 30 seconds, see if anyone can spot this, the bug in this Gradle config. Again, it's the most simple possible Gradle config. I'm writing a custom task to depend on the source folders, walk the source folders, count the number of lines by reading each file and adding them up and writing them to a resource file. In this case, it's called line count.txt and generated resources. So there's a bug here. It is a performance bug, so you will not catch it by testing and looking at the output. Output will be correct. It's also non-deterministic, so depending on what you're doing, it may happen or may not happen. But it's still there and it will randomly slow down your build. So the bug here is that we were declaring as an input file the wrong folder, which means that if you touch something in source main resources or source main templates or source main config, it will unnecessarily rerun this task, even though the output will be exactly the same because you only really care about source main Java. So on its own, this is not terrible. It slows it down by a bit. But the fact that no one can catch it means that over time, as people customize a build tool or your plugin authors upstream customize their plugins, these random non-deterministic performance and correctness bugs kind of build up. And that's why build tools have a reputation for being flaky or slow or both, because these bugs slip in and no one can catch them, no matter how hard you try. So that's why people often say don't touch a build tool if you can avoid it, because it's so fragile and so easy to get wrong. And this is very different from Java, which is known to be very easy and a safe language to use, with type checking, compilation, IDEs, and so on. So those are the areas where I think most build tools have trouble with, especially in the Java ecosystem. The performance, Java is known to be extremely performant. Build tools are kind of slow. The ID support in Java is excellent. ID support in Gradle or Maven is acceptable, but not great. And the usability for small projects and large projects, both are surprisingly hard. Like small projects are annoying to get started, so much so that you might just not do it or write in Python instead. And large projects, as it comes to customizability, it can be very error prone and easy to screw up, even if you're an expert spending 20 years writing Java like me. So that's why build tools are hard from a user perspective. So why doesn't someone just make a better build tool that fixes all these problems? I think the answer to that is that build tools are very hard from an implementer perspective as well. So every tool starts off simple. So like JBang is an example tool that tries to make it easy to run simple Java programs from the command line. So you can declare dependencies and Java version and stuff at the top of your file, and it'll automatically download them for you. It's quite convenient. But as your build tool gets more complicated, having one huge list of flat key value pairs is no longer enough to help manage and configure it. So you often end up with some kind of hierarchical config structure. Like this is an example GitHub Actions config, which can kind of thought of as a build tool of sorts. You can see I have multiple jobs. Each job has a users. Each job has a width. Some have needs. The users relies on the shared template. This makes if all this was one huge flat list, it'd be kind of a mess. But this hierarchy keeps things a bit more organized. But when you look at this a bit longer, or when you work with these configs, you realize that the hierarchy is really not what's important here. What's important are these variables you're defining in your build, passing them into what looks like function calls and using the function body. I'm declaring a job here and I'm referencing it here. I'm declaring a shared YAML template. I'm referencing and using it or extending it in these other jobs. So although it looks like a hierarchy, what actually matters when you're dealing with these build configs is a graph. So that's why I think build tools are fundamentally quite a difficult problem to work with, because basically every build tool is about defining these templated graph computations where, for example, if I have 3 modules here that depend on each other, each has a compile step, each has an assembly step, each has the sources and the main class and so on. I want to graph because the tool needs to know what order to run these steps in or what can parallelize and what cannot. They need to have computations because class files and jar files don't create themselves. Somebody needs to specify whether in Bash or in Kotlin or in Groovy or in Java or in C++ how these steps are run and how to create these outputs. It needs to be templated because the different modules in a build often look very similar, but they're not quite the same. So I need to be able to splat out copies of it, but tweak it as necessary. For example, foo.bar has no upstream class path, but foo does have an upstream class path. So these small tweaks are the norm in any larger build system. So there are lots of ways to do this. We saw with GitHub Actions has all of these requirements satisfied. Some tools just put this in plugins, but it doesn't actually solve the problem, because if it's hard to do this, then your plugins will be buggy. I'm sure all of you have experienced buggy plugins or slow plugins or plugins that don't work well and clash with other plugins. Because of this reason, it's hard to work with these templated graphs. And this is what makes build tools complicated. So if I look at this list of things on the left here, this is a list of things that every build tool has to do, ignoring the Java stuff. So ignoring classes, ignoring compilation, ignoring dependencies or packaging or assemblies or jar files. I need to have custom tasks. I need a CLI syntax. I need to redirect a disk. I need to have ordering. I need to be able to define what tasks do in some syntax. And there's a lot of things that a build tool needs to manage that most people kind of don't notice. But if your build tool doesn't do any of these things, you'll notice immediately. Like a build tool doesn't have parallelism, you'll notice, why am I only using one core and why is it taking so long? So if you look at the Gradle config we saw earlier, which is admittedly a bit complicated, almost all of the complexity of this config comes from satisfying these requirements, like how do tasks pass data to each other. That's why I need a special as file write text syntax. How to define custom tasks. That's why I need tasks are registered and tasks are named, and one of them to add a new task, one to override the existing task. How do I task run from the CLI? That's when you put this in a string. What needs to run in what order? That's why I have these declarations of input and output files and so on. So it's not that Gradle people want to make it complicated. It's just that a build tool domain is a complicated domain. So plugin APIs or extension APIs like Gradle or Maven become very complicated. So that's why build tools are hard for implementers as well, and not just for users. And that's why it's not so easy to just bang out another better build tool in the afternoon and go replace your existing one in Gradle or Maven that I've been using for 20 years. So next section of this talk, I'll talk about one of my open source projects. It's called Mill. It kind of explores this solution space and tries to improve upon it where it can. So Mill is a young project. It's a small number of maintainers, a few contributors. It's not as battle tested or industry standard as Maven or Gradle. But I think there are a lot of interesting ideas to it, which is why I've been working on it. For example, Mill uses this YAML config where you can say the root builder YAML extends Java module with these 2 Maven dependencies, and that's all you need to do to run your program. And you can have a test module where it extends tests at JUnit 4 and maybe its own test dependencies and can run tests as well. So for example, I can say .mil compile, run, test, assembly, run the assembly later, all the standard things. So this is, to me, I think a lot easier than trying to bang out a big Maven pom.xml or set up Gradle with this variety of different config files you need to configure. So Mill also has a programmatic syntax. I show this on the left. So this syntax on the left is identical in meaning to the syntax on the right. It's a bit more verbose. So the programmatic syntax in build.mil files rather than build.mil.yaml, this uses the Scala syntax. So it's a bit different from Java or Kotlin or Groovy, but hopefully it's similar enough to be understandable as packages, imports, singleton objects with extending classes, method definitions in DEF, and so on. So all this standard JVM stuff, just with a bit of different syntax like DEF to define methods. And I guess the last syntax that MIL provides is a single file script syntax, which is quite handy for small applications. In this case, if I have this web HTML scraper program on the bottom right, I need a dependency on JSoup. I can just add it as a header comment in the top using this // pipe syntax. So this header comment is a YAML, identical to the YAML syntax we saw here, but we just let you put in a single file, so it's much easier for you to write these small utilities in Java without having to set up a whole project and folder structure and everything, just to run a small piece of code. And again, like any other project, you can run webserver.java, compile, you can run it with some arguments, you can run the assembly later, and so on. So all that's the normal stuff that MIL does. I think what's interesting is where MIL tries to improve upon the existing build tools. So we talk about performance, ID support, and usability. So in performance, to compare this, we took the Netty project and took some other projects as well. These are open source projects that I don't control, but I just, as an experiment, I ported them from Maven or Gradle to MIL just to see how it compares. So Netty, I saw earlier, 500,000 lines of code, 50 sub-projects, not a small project. I ported it to MIL manually. We have some automation to help, but it still needs to be touched up manually. And we got all the tests passing in both Maven and MIL, so it's quite a realistic port and not just like a small demo. Once you got all the tests passing and know the port is complete, we can run some benchmarks and compare the performance of doing the same thing in Maven and MIL. So one of the things I noticed quite early on is that it just seems a lot faster to run, like, for example, compilation, clean, incremental, parallel, or sequential in MIL than in Maven. So earlier we saw it took about 50 seconds to run a parallel clean compile on Maven for this project. In MIL, if I do /mil clean and MIL compile, I'm still in Netty code base here. So clean, and now it's compiling. So I've actually gone through the logs and counted the number of lines of code. It says compiling adds up to the same number. It's compiling the same set of files. Instead of taking 50 seconds, the first time I run this, it takes 17 seconds. And MIL runs on the JVM, so the second time I run it, it should have warmed up and be a bit faster, hopefully. So just about 10, 11 seconds second run. So there'll be some variation, but basically it's just a lot faster to do many of the same things in MIL than with Maven. Like not just like 10% or 20x faster, but like 4x, 5x, 6x faster. So a 50-second workflow in Maven can turn to like a 10-second or 9-second workflow in MIL. And it's not just it's not just one workflow, but just across the board, it's generally faster. And again, it's not the only thing that matters, but it does matter. And many of the other workflows that I don't show here are also similarly faster, whether it's running tests or packaging and so on. I did a similar comparison in Gradle. We use a Mockito code base we saw earlier as the example. And the speed up is not as dramatic as in Maven. So Maven, we're seeing like 4 to 6x speed up versus Gradle, we're seeing maybe a 3 to 4x speed up. So Gradle is faster than Maven in many cases. It has many other trade-offs, but in many cases it's faster. And MIL is just, again, a bit faster than Gradle is. So performance isn't anything. There's some other nice features I won't go into too deeply, but I think it's just interesting to see if you use the JVM as it's meant to be used, like as a long-running hot daemon with a chance for the JIT optimizer to kick in, it can be, there's a lot of room to improve upon the performance and kind of slowness you see in existing Java build tools. Like all this kind of latency and sluggishness is a function of the build tool and not of Java itself, where Java, the compiler actually is very fast and very performant. Next, we'll talk about IDE support. So to compare this, we took the same project built using Maven, using Gradle and MIL, and you can see how it works in the IDE. So on the right, we saw earlier the Mockito error-prone submodule configured using Gradle, and we talked about how you jump to definition, you go somewhere, but not anywhere useful. On the left, I have the same sub-project configured using MIL. Again, I got all the tests passing, so there's quite a realistic port of the same build config. So the first thing you realize is that it looks largely the same. Like all of these, here it's called fork args, here it's called JVM args, here is plus equals, here is plus equals with a sequence of elements. But apart from these syntactic differences, it's largely the same contents, the same Java C options, same fork args, same internal and external dependencies up here, and so on. So it's a build tool, but still needs to manage the same kind of domain and requirements as other build tools do. I think what's interesting here is that although the content is very similar, rather than using global mutable variables like we see here in Gradle, Mill is configured using method definitions and overrides. So in Mill's Scala syntax, def is a method definition. You can see IntelliJ can recognize it here as an override and tells me where it's overridden from and can let me jump to those overridden methods. So not only can I ask IntelliJ, like, what's a Java doc for this and get something useful, I can also go to the overridden member and see what value was there before. So again, this is Scala syntax, might be a bit unfamiliar, but you can see this is a method. Method signature is a sequence of strings. The body is a task with an empty sequence of strings as a previous value that I overrode. So you can, even if you didn't know the syntax, you could probably guess what this does and guess correctly. But I think that the syntax is not the interesting part. The interesting part is that because all of these are just methods, IDEs are very good at working with methods. So for example, I can find usages here, like that. I can see where this fork args gets used throughout my build system, not just within my own config, but how it gets used upstream. So for example, if something's misbehaving, I'm wondering, why is my fork args not being applied? Why is it being applied differently from what I expect? And maybe ChatGPT can't figure it out, or it's hallucinating, and Google isn't finding anything for you. You can dig in and just like dig through the program, just like any other program you've used. So I can see fork args is used in runner. Runner is used in run background task and run fork task. Run fork task is used in run. And any of these things I can jump into, right? So if I want to see what is runner.run, I can jump to it, see its parameters, types, default values, and so on, and navigate around this program. That's navigating downstream. I showed you navigating from fork args to runner. The other thing you often do is navigate upstream. Like, what is this and where does it come from and how did it come to be and that I'm using it? So for example, let's look at final main class. Let's say there's no documentation, which is often the case in many real-world code bases. In Mill, that's not a problem because you can just jump to it. No docs, but there's implementation. I can see delegates this final main class opt thing. If there's a write of it, I use that value. If there's an error message of some kind, I report an error. So again, the syntax may be a bit foreign, but you can kind of guess what this does. And again, let's say I don't know what final main class opt is. And let's say there's no documentation or the ID is not working right. I can just jump to it. No docs, that's bad. But I can see the implementation. I can see that, well, main class is tried first. Is any explicitly specified main class? If there is one, I use it. If there's none, I try looking at all local main classes. This is any main classes detected by looking for public static void main methods in the bytecode class files. If there's an empty sequence, I report an error, no main class found. If there's exactly one, I use it. If there's multiple, I report an error saying that, oh, we found multiple main classes. Please tell me which one to use. So what's interesting is that this is not anything new. This is exactly what you do every day in any real-world code base. Like any real-world code base doesn't have perfect documentation. Many of them are proprietary. You can't find them on Google or ChatGPT or Gemini. But nevertheless, you somehow can still navigate your way around. It's largely because of your IDE that helps you. So what Mill does is that because Mill lets you define your build config using method definitions and method calls rather than these global mutable variables, it means IDEs, which are very good at navigating around method calls, are very good, out of the box, very good at navigating around Mill builds, even without any special Mill plugin in IntelliJ or something. Like there is no Mill IntelliJ plugin, there's no Mill VS Code plugin. But because they know how to work around method calls and objects and classes, they are very good at navigating around your Mill builds in a way they cannot do so in, for example, Gradle or Maven. So that's the ID support angle, where I think Mill does something quite interesting and quite different from what's there before. Last thing I'm going to talk about is the usability angle. So I think to start off with, the fact that Mill can turn this Maven config into a single comment at the top is very handy, and the fact that you can just /mill run it from the command line is also very handy. There are many cases where you want to write a small script, and maybe you're using Java for existing project, or you learn Java, or you're more familiar with Java, or there's some library in Java you want to use. For example, JSoup's a library you want to use. So you may not want to write this in Bash, and you may not want to write this in Python or Ruby. But if you had to write this kind of build tool boilerplate every time you write a small program, and every time you want to run that small program, you probably wouldn't write it in Java. But with Mill, you can just write it in Java and run /mill foo.java with passing in arguments. And this makes it very convenient, even if you're using third-party dependencies, specific JVM versions, and so on. makes it very convenient to just write code and run it without having to worry about how am I going to get started with my build tool. We saw that earlier. On the more advanced side, if when customizing a build tool in a larger project, I think where it's different is that where most build tools need you to learn a special plugin interface or plugin API, a mill lets you just write code to do the thing you want. Like there are plugins, you can use the plugins, but sometimes if the plugin doesn't do what you want or you can't find a plugin, the plugin's not quite perfect for your use case, you can just do it yourself, and it's often quite easy. So I can show you this to you live. So let me just go to the right folder. Java custom. Make it a bit bigger. So over here on the right, I have like a small mill config using the programmatic syntax for a minimal Java module. I say object foo extends Java module. This is a singleton object. So the foo subfolder in my project is a Java module and inherits all the compile resources, tests, and so on from the upstream Java module class. So I can compile it, and there's some source code in here I'll skim over. But let's say I didn't want the defaults. So over here, there's nothing, but let's say I want to customize it. How would I do that? Maybe I wanted to count the lines of code in this module and add it as a line count resource file like we saw earlier. So in Mill, everything's a task, and every task is a method. And the way you write methods in Mill's programmatic Scala syntax is def. So I can say def line count equals a task. And within this task body, I can call other tasks. For example, I can call foo.sources. Or if you're not sure which one to call, you can ask IntelliJ get ID support here. So in this case, maybe I want all individual source files fed into the Java compiler. I can map this to every file. I get the file path. I read the lines of this file and get the size. And I sum them up. So this is all you need to define a custom task in Mill. So again, the syntax is might be unusual. It's def rather than public static blah, or in Kotlin fun blah. But the idea is that I just define a method. That's a task. I can call other methods like foo.all source files, and I can transform it using your standard like map, sum, any programmatic code you want to write. So now I can do mill show foo.line count. You see this program has 17 lines. I can do inspect foo.line count. You can see we automatically capture things like the upstream tasks for you, so you don't need to explicitly register them like in Gradle. We capture the Java doc for you, and we capture the name of the task for you based on the method name and module name, so you don't need to have a separate string there giving you the module name of that task like in other build tools. So all quite convenient, and just like in 4 lines, we have a custom task. But we haven't yet wired it into our program's resources yet. So in Mill, again, everything's a task. Resources are also tasks. Tasks are methods. Where you customize the existing method is often by overriding it and either calling super or just replacing it wholesale. So in Mill, I can customize my resources. I do override def resources. Again, you're not sure which one you want to use. You can ask IntelliJ. It'll give you the docs. I can call super. And then if I can also write to this task or destination folder, which I'll explain in a moment, my line count has a string. And I'm going to append a reference to this to my resources. So you may ask, like, what's this task.destination folder here that I'm using? So if I do mill show foo.resources here, you'll see that I have my foo/resource folder. That's my original resource folder I kept around because I called super and returned it. But I also have this out/foo/resources.des folder, which is this task destination folder. So the purpose of this is that the problem that this solves is that in any build tool, the file system is basically the world's biggest global mutable variable. Like anyone can write to anywhere in the target folder, anyone can read from anywhere. You don't know what you can delete safely without screwing up your build. You end up having to clean install every time because the different plugins have screw up and stomp over each other in the target folder, don't invalidate properly when they should be invalidating. Then it becomes a big mess, all because it's a global mutable variable. No one knows who depends on what or what needs to be run first and what needs to run after. So to try and mitigate this, Mill says that you don't write anywhere in your output folder. In Mill, it's called out. But rather, any task writes to its own destination folder, in this case, out/resources.dest, out/foo/resources.dest, that is unique to that task. So rather than being this big global mutable file system that gets very messy, you have these locally mutable but encapsulated folders where only resources can write to resources.desk and other tasks can only read from it. So this is the kind of encapsulation that's common in any object-oriented program. Like you keep the mutability hidden private, you expose a read-only kind of interface to the rest of the program. And the build tool makes it much easier for both humans and the tools to figure out what's going on. Like if I wanted to see what the output for foo/resources is, I don't need to look at every single file in out. I can just look at out/foo/resources.desk and output will be there. It must be there. It cannot be anywhere else. Now that I have this, I can do foo.run. And you can see that I'm able to use this resource file that I generated at build time. I can see the line count.txt. See the files on this there, and my program is able to use it at runtime. And then there's caching, there's parallelism. Line count will be evaluated in parallel with compilation because it doesn't depend on each other. And I think what's most interesting here is that when you look at this code, although the syntax may be a bit foreign because of Scala syntax rather than Java, Kotlin, or Groovy, the concepts are all very boring. This is a very standard object-oriented program about singleton object that extends a class. I define a new method that calls another method. I override the method and I call super and I call the other method and return the value. The return keyword is optional, so the last thing at the bottom is just returned. So you just need to write normal object-oriented code and you get kind of interactive build tool configuration pipeline just out of the box, basically for free. I think that's pretty cool. So you don't have this like learning about the API, plugin APIs and plugin infrastructure that you often have in many other build tools. So that's the performance, ID, support, and usability angles, where I think Mill is pretty cool. Like it's definitely not as battle tested for 20 years as other build tools, but there are these areas where it has a lot of interesting ideas that I think can do better than many build tools have been doing in the past. So lastly, I'm going to talk about the interesting ideas behind Mill, which is this idea of object-oriented builds. So the obvious question now is, if Mill can do this, why doesn't Maven or Gradle or Bazel or other build tools just do the same thing? Like, why can't they all get perfect ID support, easy customizability, and like great performance? I think it comes down to this idea of object-oriented builds. So earlier we talked about how these templated graph computations are what makes build tools complicated. If I define the public class templated graph computation, or you define the public class templated graph computation, it's going to be a very complicated class. It has a lot of different API surface area and can be very hard for someone to learn. But it turns out that every person who's been using like Java has been writing templated graph computations for many years or decades by this point, because that's exactly what object-oriented programming is. Object-oriented programming is all about templated graph computations. So if I look at object foo extends Java module, there's a singleton object extending a class. I don't need to teach you anything to know that the object gets all the methods from the class, and the methods will return values to each other. So foo.sources gets called by foo.compile. Compile gets used by class path gets used by assembly to get the resources, all the standard method call graph that any object-oriented program has. And if I add a new method, def line count equals task, all source files dot map some blah, and I override the method, override resources, and I call super, and I also call line count. I don't need to teach you anything for you to know how this works. Like, I don't need to teach you anything for you to know exactly how this will affect the graph you see in the top right, because this is exactly how OOP works in Java, in Kotlin, in Scala, in Python, in JavaScript. Any language of OOP, it works like this. And once we have last thing is, if you want to template the graph, I can turn foo into a class, or in Mill syntax it's called a trait, but it's basically the same thing. It's a class. And I can inherit it in two different singleton objects, and I have now templated my graph. And all your standard OOP techniques work. You can have subclasses with customizations that you use in a few places. You have subclasses. You have override. You can have super. Everything works in everything from OOP applies to how you template graphs in Mill. So you don't need to learn a whole new API like you do in Gradle or other build tools. You just write objects, classes, methods, method calls, and overrides, and it just does the thing that you already know what it's going to do, because it is an object-oriented program. And once we have this graph, Mill can then do the build tool stuff. And Mill can say that compile and line count can run in parallel because they don't depend on each other, but assembly needs to wait for them both to finish before it starts. Mill can say that foo.line count, foo.compile, foo.assembly, these all already have fully qualified names on the JVM. We can just use those names on the command line without having a separate string that's the name of the task. And can use the same names to assign every task a unique location on disk to put its JSON out metadata and a destination folder to put its file outputs. And these will never collide because methods on the JVM will not collide to a first approximation. And Mill can do incremental invalidation, like if you touch a resource folder, it's easiest to do a breadth first search, see that these resources and assembly needs to be regenerated. Compile and line count does not need to regenerate. Mill knows where to find a previous output for compile and line count because it's in a standard location. So you don't need to tell Mill where to get it, Mill already knows. And Mill knows where to find a previous output for assembly, so you can go delete it, again, because it's a standard location. So Mill can delete it and regenerate the assembly from scratch. And the thing here is, again, there's no code here related to dependency tracking, parallelism, or caching. You don't see depends on clauses like in Gradle. You don't see phases like in Maven. You don't see threads or locks or semaphores or mutexes. You don't see cache key computation or cache invalidation. All that's handled behind the scenes 99% of the time. And you just write what's really quite a boring object-oriented program on the left. And Mill turns into a build tool and does all the build tool things for you more or less automatically. So if you look at all these concerns that Gradle needs to satisfy and makes Gradle complicated, Mill also needs to satisfy all the concerns, but it kind of squeezes it into a much smaller package. So like how are tasks run from the CLI? Well, you already have a method name, so we use a method name. How do you define your own custom tasks? It's just a method. What needs to run what order? How do tasks pass data to each other? What task depends on what? All this is answered by what task, what method calls what other method, and returns a value to the other method to use. So Mill does have answers to all of these. It's just the OOP answer rather than the custom templated graph API answer that many other build tools make you use. So this is the idea of object-oriented builds. It's just the idea is that a build is just methods, objects, classes, extends, override, super. Everything that works as you expect from Java 101. Everything works as IntelliJ expects. That's why IntelliJ can navigate all this stuff without having a special Mill plugin to teach it how it works. Mill handles all the build tool stuff for you, which means you often get better performance because you don't have plugins for getting the cache or parallelize things. You don't need to clean like in Maven. You have Maven clean installed because you don't have plugins screwing up the cache key computations and cache invalidation. It just makes life easier for everyone, so you can work on fun features, tooling integrations, or application code rather than struggling with your build config. In terms of tooling integration, because it's so easy to customize Mill like we saw earlier, we've taken liberty of extending Mill to have built-in support for many of the existing open source projects. All your linters, in all the JVM languages, Java, Scala, Kotlin, Android, all the linters for these, all the publishing destinations, all the packaging workflows. So it's quite easy for us to do this because Mill is easy to extend. And hopefully there's something on this list that's something that's not on this list you need. It will be easy for you to kind of customize your own build to include it, whether you need Vardin support or Quarkus rather than Micronaut. Hopefully you can just do it yourself using the techniques I showed earlier. So that's the idea of object-oriented builds, which I think is very cool. Like it's easy to say, I'm just gonna put in more effort to make the build tool better, like the ID support or the performance or whatever. I think the reason why Mill's been able to get a lot of these interesting results, like good performance and good ID support, is because of this foundation where it treats a build as an object-oriented program, and everyone, both humans and IDEs, know how object-oriented programs work. And that just makes life simpler for everyone. So this is the last slide. This summarizes everything we talked about. I won't read it out. I guess the long and short of it is, any of you have had problems with existing Java build tools or running Java code and want to make it easier to work with small Java programs and large Java applications, I encourage you to try out Mill. It's definitely less battle-tested than Maven or Gradle. It's only a few years old rather than a few decades old. But it has a lot of interesting ideas, both for small builds as well as for big builds. And these interesting ideas translate into real user-facing improvements in performance, ID support, and ease of use. So the projects at millbuild.org that's getting started in Java, Scala, and Kotlin, and hopefully most of the things you care about will be here. Like if you want to see how Spring Boot works in Mill, there are Spring Boot examples. You want to see how packaging and a Gradle native image works in Mill, or publishing the Maven Central works in Mill. We have docs and stuff here. So I encourage you to try it out and let us know on the GitHub Actions or on Discord how it goes. And that's the end. Thank you.
All right, well, thank you for the presentation. And do we have an update on the?
I haven't heard anything about the teaser.
Okay, so does anyone have any questions for the speaker?
I was going to ask about this build language that you've created. You say it's a variation of Scala?
Yes.
Okay. I guess there's no way you could just use Scala itself. Because you have to compile Scala. You have to build the build before you can build program, I guess. So you more or less have an interpreted version of Scala.
It is just a Scala compiler. So I didn't write my own interpreter. You just download the compiler jar and you compile the file. It's the same how Gradle works with Kotlin. It downloads a Kotlin compiler and runs it, and there's not really any problem because build tools are good at downloading things to run, right? Like that's what build tools are all about, downloading dependencies and running them. So downloading the Scala compiler and running it to compile your build file is straightforward.
So it's downloading Scala to be able to accomplish what it's doing.
Yeah.
Things like, because I was wondering how in the world could the IDE make sense of this mill language that you come up with without some plugin or compiler?
Because IntelliJ
magically, how does it know?
Because IntelliJ knows how to work with Scala and all of its details.
It's because the IDE already understands Scala.
That's right.
Understands mill.
That's right.
Okay.
Yeah. So IntelliJ and VS Code, I think, work out of the box. And Eclipse, there's a plugin to make it work. Yeah. And someone's been working on NetBeans support.
With the extension, like, because the fact that it's a .mil file.
I sent one pull request to JetBrains to add that. So as of like June this year, it does it automatically. Yeah. Previously, you had to customize yourself in the extension associations.
Do you have a wrapper, kind of like how Gradle and even Maven, I think you do like a wrapper script?
Yes, yeah. So this / mill you see here is the wrapper script. So it's there's a Windows and there's a Unix version. There's a Unix version, and it's the same. So it's also the same benefits, right? You always use a correct version of mill and correct version of Java. You never get these weird conflicts you get in other if you don't use a wrapper. Yeah.
You mentioned GitHub Actions. Are there any other like CI/CD pipelines that this can work with? Can it work with any of them? Is there anything special that goes into this just sort of a build pipeline?
So the special thing about this is that it doesn't require any installation. So similar to Gradle or Maven, use a ./Gradle w /Maven w.
Okay. Just having a script checked in. Code.
Different from Maven or Gradle, it doesn't even require Java installed. So it will bootstrap the JVM if it doesn't have one. You know how Maven Gradle can already download JVM for like sub modules and stuff. So this one can also download it for the main build system. So you run it on a clean Windows or clean Mac or Linux machine, and it should just work as long as you have the ./mill script or ./mill.bat available. Yeah.
So in some sense, I like what you built. I think that you kind of solve the problem by leaning into Scala and parallelism, whereas someone the powers that be at Oracle they have unduly influenced people to build older build tools in Java or whatever. But so people are stuck on their existing build system, right? It sucks, or they parallelize it using Kubernetes or something instead of using a build tool that works well for them. So what's your approach for getting more people to use this instead of just having yet another standard that's another 20% of the market?
I mean, everything starts from a small project, so I can't overnight turn into a 90% market. I mean, what I've been doing is I've been trying to talk about it so people know about it, and we also have some we have some automated tooling to help with the migration. So we look at migration, there's both docs for migration as well as automated migrations from Maven or Gradle or SBT. So these automated migrations are not 100%. They'll get you like 90%. You might have to tweak it a bit yourself, but hopefully makes it easy. So rather than taking a week to migrate, it might take a few hours to migrate the project from Maven or Gradle to Mill. Yeah.
So just to follow on to what Genesis said, in terms of the adoption, so I've only played with Scala. I just like fully embrace it. But like Mill versus SBT, like you working with the Scala community, I think it seemed like a pretty, like in terms of adoption, because I know at least what I've read about, and again, just me dabbling with Scala, like I've never had a complicated SBT build.
Yeah.
But I've heard like this pain with SBT, so I was curious, like feedback from the Scala community of Mill versus the older, the tri-tier SBT.
Yeah. I think the long and short of it is they like it. Like I haven't got any negative feedback from it. Generally, people are quite happy with it. Yeah. I think SBT has a very similar kind of it's very similar to Gradle in a way. It's extremely flexible and can do a lot of things, but it's also very confusing. It's confusing in different ways, but they're both similar in that they're both confusing. I think people do like it from the ones that have tried it. Yeah, it's obviously not the biggest build tool in the Scala community, but it's I think there's
SVT is like a DSL, right?
Yeah.
Yeah, like it's like kind of Gradle, like.
Yeah, so SVT it's a bit fancier than Mill's syntax.
Language of the build.
Yeah.
itself versus
That's right.
pure Scala. Okay.
Yeah.
That's neat.
Yeah. Any other questions?
But Scala, as I understand it, is kind of a hybrid language in that you can do a functional approach rather than just an object-oriented approach, right?
Yeah.
So you keep talking about using object-oriented programming. Could you not do this with functional programming? With this.
Yeah, I mean, for Mill, it does both. So I guess the important thing about functional programming is your functions are pure and do not have side effects. That's the kind of key idea, and that lets it easy to reorder them, parallelize them, rerun them, or cache them, and all sorts of things that you cannot do with a side effecting function because you can't parallelize things if you're going to stomp over the same file and affect each other. And that's largely what Mill tries to do with its tasks. So like for example, the destination folder I mentioned earlier is largely an attempt to make the I/O of any build tool, and every build tool is full of file system I/O. Try and make it a bit less unconstrained and tame it a bit so that you don't have anyone stomping over files everywhere. But I write to my own thing and then I freeze it, and other people can only read it. So I talked about object-oriented style, but the fact that every task returns its value and doesn't write over random files anywhere in the file system, that is very much a functional approach. At least it's a baseline of functional programming, right? Like, the task has no side effects, therefore I can cache it, parallelize it, rerun it, and all that without having to worry or skip it if it's not being used. It doesn't use the more advanced functional stuff, but maybe you'll need to. Yeah. Cool.
All right, are we ready to shut down the recording? Move to the raffle?
No questions, anything from the online?
Two questions.
Okay.
Okay, when we get to the recording,